It may not look like much, but herein lies a particle that has massive ramifications for the world of physics. This is the muon, a close cousin to the electron that you are likely familiar with. Unlike the electron, however, the muon only has a lifespan of about 2.2 microseconds. Luckily, muons are not rare and can be easily produced in radioactive decay. As I was saying earlier, they are close cousins of the electron. Muons have the same charge, same spin, and everything else in common with the electrons, except notably a heavier mass. Recently, muons have become the focus in a field known as quantum electrodynamics. This field seeks to understand how charged particles interact with magnetic fields. This is simply an extra layer to classical electrodynamics, which explains simple interactions with magnetic fields. For example, a compass needle interacting with the Earth's magnetic field. The strength or torque of the needle as it aligns with the magnetic field is defined by the needle's dipole moment. Usually, the stronger the magnet in the needle, the stronger its dipole moment. This same principle, coupled with quantum mechanics, can be applied when working with charged particles like electrons and muons. Their dipole moment is defined by this equation, where S represents the quantum spin of these particles, which all electrically charged particles have. There is additionally this G factor, which is a measure of proportionality between the spin and the dipole moment. What scientists have discovered is that their theoretical values for the G factor of the muon were not aligning with their experiments. According to QED, they should expect a G factor of 2. However, the experimental value was slightly above 2. One error in this prediction was a lack of regard for the standard model of physics, which can slightly affect interactions like these. Armed with QED and the standard model, researchers were sure they had found the solution. However, even when accounting for the standard model, researchers found the experimental value to still be higher than expected. This discrepancy has led many to produce their own hypotheses. Renowned scientists believe this indicates the existence of a fifth fundamental force, not yet accounted for in our standard model. Physicists hope this will allow us to move closer to a theory of everything, a model that comprehensively and reliably explains all of physics. This theory of everything relies on mending two separate spheres of physics, the standard model and Einstein's theory of gravity and general relativity. Until now, both theories have been woven incredibly tight, but possibly the muon may reveal a gap for the two to mesh together, a discovery which would certainly be tremendous news for our understanding of physics.